Hi everyone, my name is Maxence Faldor, and today I'm presenting MAP-Elites with descriptor-conditioned gradients and archive distillation into a single policy. Work done in collaboration with Félix Chalumeau, Manon Flaja, and Antoine Cully. Our method, named Descriptor-Conditioned Gradient MAP-Elites, or DCG-MAP-Elites, improves MAP-Elites algorithm by combining the directed search power of policy gradient methods stemming from reinforcement learning with the exploration capabilities of genetic algorithms, enabling the evolution of large neural networks. Optimization is ubiquitous in science and engineering, and recent progress in artificial intelligence has enabled to find high-performing solutions in vast search spaces, leading to the mastery of complex games like StarCraft and the game of Go, or the creation of new technologies like ChatGPT and DALL-E. In optimization, we try to find in the search space the solution that maximizes an objective function. However, for challenging problems, the objective function may be difficult to design. But even when the objective function is obvious or given, the fitness landscape, like the one shown here, is deceptive. And following the objective with gradient-based methods, for example, will get you stuck in local optima. That is because the objective function fails to reward stepping stones that are necessary to reach your goal. Finally, following a single objective and returning one single solution like traditional optimization methods can lead to a lack of exploration of the search space. Finding the one best solution at doing one thing is very brittle in real-world environments. In stark contrast, a fascinating aspect of biological evolution is its ability to generate a wide diversity of species. Inspired by this idea, quality diversity algorithm aimed to generate a collection of diverse and high-performing solutions. The performance of a solution will be given by the fitness function, F, and a solution will be characterized by its descriptor function, D. The goal of quality diversity algorithms is to find the highest fitness solutions on each point of the descriptor space. For example, in robotics, we can use QD algorithms to generate a large collection of diverse controllers that work differently. You can see here the diversity of solutions found by the algorithm. And then we can search the collection of controllers to choose the best one to adapt to damage. For example, this robot is still able to walk using a controller that doesn't use the damaged leg. Now, let's go through a quality diversity example. Here, we consider a locomotion problem called walker, where the goal is to go forward as fast as possible while minimizing energy consumption. A solution is described by the gait of the robot. In practice, we use the feet contact rate ranging from 0 to 1 for each foot. So a solution can have a descriptor of, let's say, 80%, 60%, meaning that the right foot is in contact with the ground 80% of the time, and the left foot only 60% of the time. When the descriptor space is two-dimensional, like here, we can represent the collection of solutions generated by the QD algorithm like this. On each point of the descriptor space, the brighter, the fitter, and blank means no solution has been found for the corresponding descriptor. Now, if we take a look at different solutions at different places in the archive, we will find a lot of diversity. For example, this one is close to the max fitness solution and is using equally each foot. This one is keeping one foot always in contact with the ground. This one is doing the opposite. It's keeping one foot always up in the air. You can see that its fitness is greatly impaired. This one is dragging both its feet on the ground. Now let's have a look at MAP-Elites, which is a very simple yet very effective QD algorithm. MAP-Elites starts by discretizing the descriptor space into a multidimensional grid of cells initialized with random solutions. Then the algorithm consists in a loop of 1. Genomes are selected from the archive. 2. Genetic algorithms variations, or GA variations, are applied to the genomes, for example, random Gaussian noise. 3. Offspring are evaluated to get their fitness and descriptors. 4. Offspring are added to the archive. A solution is added to the archive if the cell corresponding to the descriptor is empty or if its fitness is better than the current solution in that cell. The goal of MAP-Elites is simply to return an archive that is filled with high fitness solutions. MAP-Elites works very well and has been applied to a variety of problems. However, MAP-Elites relies on genetic algorithms variations that may cause slow convergence in high-dimensional problems due to a lack of directed search power, and thus is performing best on low-dimensional search spaces with open-loop controllers. So the question is how to scale to deep neural networks with thousands of parameters. When the problem can be formalized in the reinforcement learning framework, we can combine the directed search power of gradient-based methods coming from reinforcement learning with genetic algorithms to get the best of both worlds. Recent works have tried to combine RL with QD and created a field that is called QD-RL, giving rise to several algorithms like CMA-Mega and QDPG. For example, here, the data generated at the evaluation step can be stored in a replay buffer and then be used by an RL algorithm to train an actor and a critic. The critic can then be used to derive policy gradient variations, or PG variation, applied to the solution in the archive and generate new offspring. This algorithm is PGA-MAP-Elites, and it has been published at Gecko in 2021, and it is performing very well on QD benchmarks. PGA-MAP-Elites outperforms MAP-Elites on complex environments with high-dimensional search spaces, and is able to evolve neural networks that perform different gates in environments like Hopper and Ant. On this archive comparison between PGA-MAP-Elites and MAP-Elites on Walker, you can see that PGA-MAP-Elites massively outperforms MAP-Elites. However, PGA-MAP-Elites suffers from a severe limitation illustrated by the next slide. Consider now a locomotion task like Ant, where the fitness is the opposite of the energy consumption, and the descriptor is defined as the final position of the agent. We sample a solution from the archive with descriptor 30-9, for example. We take its genome and apply a policy gradient variation. And we obtain a solution that is super high fitness, but it does not move at all because it is minimizing energy consumption. And by the way, this is a video on the right. With the PG variation, the descriptor of the parent solution collapses on the descriptor of the global optimum at the origin. So the offspring are discarded and no interesting solution is found, thereby hindering fitness and diversity. If you remember my introduction slide, this is a clear example of the limitations of objective-based methods creeping in. You try to follow an objective to find a good solution, but it induces a lack of exploration. It works against diversity. The initial goal of the method was to combine diversity search with the gradient-based optimization to get the best of both worlds, but in this case, it clearly fails. And we end up with a combination that does not synergize very well. And you can see that on Ant Omni, PGA-MAP-Elites performs worse than MAP-Elites, despite the use of super expensive policy gradient variations, and that's simply because the PGA variation operator here is useless. So PGA-MAP-Elites is half a MAP-Elites, because half of the offspring are wasted with PG variation that do nothing. So the main question is how to improve fitness while preserving diversity. The method I propose is an attempt to reconcile gradient-based methods, which can be very powerful in the right settings, with diversity search. Instead of applying a gradient variation that is fitness only, we want to derive a gradient that is orthogonal to the descriptor, so that when we apply it, the descriptor of the offspring isn't changed. In other words, instead of blindly following fitness, we want to improve fitness while reaching a desired descriptor. So the PG variation operator needs to be conditioned on the descriptor that we want to reach. Here, 30-9, for example. To apply a descriptor-conditioned PG variation, we need to have a critic that estimates the return, starting from state S, taking action A, and given that the full trajectory reaches descriptor D, 30-9. So we take the parameters of the solution, and instead of using the traditional critic, we want to use a descriptor-conditioned critic. We condition it on the descriptor of the solution, and applying that PG variation will improve the fitness of the solution while keeping its descriptor constant. But the question is, how to train such a critic? I propose to answer that question in the next slide. From the evaluation step, we have transitions augmented with the descriptor of the trajectory. The transitions are examples of state S in which taking action A leads you to achieve descriptor D. So for all D prime in the descriptor space, the value of the descriptor conditioned critic conditioned on D prime must be equal to the traditional critic if D is equal to G prime and 0 otherwise. We can rewrite this expression like this with a similarity function S It's simply defined as 1 if d is equal to d prime and 0 otherwise. By definition, the traditional critic is equal to the discounted sum of rewards starting from state S and action A. So by substitution, we can rewrite the descriptor-conditioned critic like that. Finally, by putting the similarity function inside the sum, we obtain the following expression. Now, let's look at the bootstrapping target for the descriptor-conditioned critic. For a normal critic, the target Q value with the bootstrapping is equal to Y is equal to the reward plus the next Q value. So by identifying the terms for our descriptor-conditioned critic, we have the target Y that is equal to the reward scaled by the similarity function plus the next Q value. So the target is the same, except that the reward is scaled by the similarity function. Actually, it is not exactly the same, because now the critic is conditioned on the descriptor, the desired descriptor, but the actor must be as well. So the actor does not estimate the best action globally anymore. It is estimating the best action given that we want to achieve a descriptor D. In DCG-MAP-Elites, the transitions generated at the evaluation step from the solutions in the archive are stored in a replay buffer. Then the replay buffer is used to train an actor and a critic. Notice that compared to PGA-MAP-Elites, now the critic and the actor depend on a descriptor. It means that at the end of training, we can choose a descriptor, give it as an input to the actor, and hopefully, if the actor has been properly trained, achieved that desired descriptor. It means that the solutions from the archive are combined into a generalist actor. In other words, we distill the knowledge of the archive into the actor as a byproduct of the actor-critic training. In downstream application, instead of switching solutions to achieve a different behavior, we can now simply change the descriptor in input of the same policy to achieve a different behavior. So that's very handy. And this happens at no additional cost because we train the actor-critic anyway. Now let's take a look at the experimental setup. We evaluate our method on 4 QD tasks. In omnidirectional tasks, the goal is to minimize energy consumption, and the descriptor is the final position of the robot. In unidirectional tasks, the goal is to go forward as fast as possible, and the descriptor is the feet contact rate of the robot. We compare our algorithm with 4 baselines: MAP-Elites, MAP-Elites yes, and 2 MAP-Elites improvements, PGA-MAP-Elites and QDPG that focus on neuroevolution. We will compare the QD score, which is simply the sum of fitness of the solutions from the archive, and the coverage, which is simply the fill rate of the archive. On nTomni, you can see that DCG-MAP-Elites outperforms all baselines by a large margin. The fitness and coverage of our method is the best. Looking at the QD score, you can see that our method, in green, outperforms all baselines on omnidirectional tasks. On Walker unidirectional, we can see that our method achieves similar performance than PGA-MAP-Elites, in purple, where we expected no improvement. In terms of coverage of the archive, you can see that our method outperforms every baseline. We can see that DCG-MAP-Elites has a better coverage than QDPG without explicitly promoting diversity like QDPG does. So that's the evaluation of our method, but we can also evaluate the archive distillation now. Our descriptor-conditioned actor is now comparable to an archive, so we can define a QD score for the actor. To do that, we evaluate the actor conditioned on the descriptor from the solution stored in the archive. As a proxy for coverage, we compute the descriptor error mean, which means that we evaluate the mean distance between the conditioning descriptor and the observed descriptor. For the QD score, we can see that the descriptor-conditioned actor has similar performance as the archive on n tasks. However, it performs worse on Hexapod and Walker. For the descriptor error mean, we can see that the actor is a bit less accurate than the archive on all environments. In conclusion, we propose an algorithm that combines fitness gradients with diversity search. In contrast with previous methods, fitness and diversity finally synergize. DCG-MAP-Elites significantly outperforms all baselines on omni tasks. The directed search power of policy gradient methods enabled to find high-performance neural networks to solve continuous control tasks like ANT or Walker. But in a deceptive environment like NTRAP, the algorithm does not get stuck in local optima, like traditional reinforcement learning methods would, because it combines the policy gradients with diversity search. And DCG-MAP-Elites maintain state-of-the-art performance on tasks where we expected no improvement, like Walker. And the cherry on top is, at the same time, the knowledge of the archive is distilled into a single policy. And the archive distillation happens as a byproduct, so there is no additional cost to that. So that's DCG-MAP-Elites, and thank you for your attention.